The time it has come, and I am welcome to our digital stage. For me, the queen of lean software development, Mary Poppendieck, and she will share with us will give us the glance of what awaits us, the future of software engineering. Mary, the stage is yours.
Thank you very much. I'm going to start actually by talking about the past, because that's a really good way to think about how things evolve towards the future. So
Mary?
Yes,
you need to share the screen if you want.
I need to share it again.
Yes, yeah, because we changed. Yeah.
All right, I will do that.
Mm-hmm.
How's about that?
Yes, we see it.
Okay. All right, now let's start all over again, and I'll talk about the future of software engineering by starting in the past, because the future is generally following on in the path of software engineering. So if we take a look at 1999, that's not the dawn of software. I was already programming for something like 30 years by that time. But it's 1999 and Google is just a few months old. It was founded in the late 1998. So you can tell that things are about to change, but we didn't actually know it. What's been going on over the last decade is that open source, especially Linux, has become a very important operating system. It's starting to run servers around the world, all kinds of software. And this is not paid software. It's weird because it's open source and it's all volunteer and it works so well that enterprises can depend upon it. And that's a big surprise to a whole lot of people. And in 1999, Eric Raymond published The Cathedral and the Bazaar to sort of explain what was going on. So if we take a look at The Cathedral and the Bazaar, it says, up until now, we have thought of software like a cathedral. A cathedral, this cathedral actually, unfortunately, is not quite the same today, but come on, let's go. But if we take a look at a cathedral, it has an architecture. It can be very big, but it gets to a certain point where it can't get any bigger. You have to build it according to its architecture, and you have to stop when you reach the end of the limit of what that architecture can handle. It can not get any bigger. The bazaar is a little bit different. It's a bunch of small independent people working together, or little shops put up in a, like a farmer's market or something like that. And each one is independent and they do their own thing. And guess what? You get a really nice market, and it can expand all you want. And what Eric Raymond said is, we've moved to the bazaar style in Linux. It's a great babbling bazaar of different agendas, different approaches, out of which a coherent and stable system could seemingly emerge only by a succession of miracles. And you can't really consider Linux a succession of miracles. It's a different way of approaching architecture for software, and a way that actually, when you want to get really big, is the only way that works. It's horizontal scaling. So now if we go to 1999 again and look at the business software world at that time, all of the software was great big monolithic systems, very slow to change. You were lucky to see one release a year. There was a single integrated database. At least if you were good, you had all of your data integrated into one database. It was running on one server. Why one server? Well, there was this theorem called the CAP theorem, which said you can't have consistency, availability, and partitioning all at the same time. If you partition your database across servers, either it's not going to be immediately available or it won't be consistent between different viewers. And since you have to have consistency and availability in a database, how could you not? You can't partition your database. So along comes Google. This is their 1999 web page. They're still a young company, and they're looking over 1 billion web pages at that point in time. How do you put those on one server? How on earth? Actually, you can't. And here's what Google was thinking about. There's two ways to get a whole lot of data on computers. One is to get a bigger computer. But let's take a look at Grace Hopper, who is the person who started COBOL and a very, very renowned software engineer at the time. I actually heard her give a talk in this time frame. And she said, if one ox can't do the job, they didn't get a bigger ox. They used two oxen. When we need greater computer power, the answer is not to get a bigger computer, but to build systems of computers and operate them in parallel. That's the strategy. And it's not like people didn't know it. It's like people weren't doing it because the CAP theorem kept them from it. So your option here is to scale horizontal. And if you take a look at what Google did, they had some hardware that looked like all kinds of individual servers connected together. This is their 1999 first set of servers. This was radical at the time. Really getting all these many computers working together was something nobody had actually figured out how to do. Now in 2000, the year 2000, there was a crisis at Google. And indexing software, which ran across all of those computers, stopped working. And nobody could figure out why. There were two software engineers that had been hired a couple of years earlier that were very renowned in the software world as software researchers. And they came into the war room and they started trying to figure it out. And after a whole lot of hard work, they figured out that the cause was faulty hardware. They had so many computers that one of them had a bad memory chip. And therefore, the indexing software would go wrong. So at that point in time, we used to have redundant computers, but the hardware was so reliable, we figured we didn't need to do that because it failed so rarely. But if you have a whole bunch of hardware, it's going to fail. So they created an architecture which was going to deal with the fundamental concept that eventually hardware fails. And if you have a lot of it, its mean time between failure will be actually pretty fast. So they created a file structure that looks like this with chunk server. Oops. I'm having trouble with my mouse here. You have a chunk server and you spread your file chunks across 3 different computers. And if one computer died, you detected that, you kicked it out and you put another one in service and then you re-replicate it across. So you always had 3 copies of things. When you want to scale horizontally across hardware, you have to have redundant hardware. And how to create a redundant database across redundant hardware was something that hadn't been figured out yet. In fact, it was figured out in the early 2000s. In 2001, Doug Cutting and Mike Carfella were on Apache, again, another open source area, and they created something called Hutch, which was a web crawler. But the problem was, once they crawled a certain number of web pages, they were just drowning in data and they couldn't figure out how to deal with it. But in 2003, the Google file system paper was published. Sanjay Gamwat was the lead author, and it talked about that file structure that I just showed you. And these 2 guys that were working on the web crawler said, oh my gosh, that works. I hadn't thought of that. And so they created something called the Hadoop file system and put it on open source. And then the next year, there was a Google MapReduce paper by Jeffrey Dean and Sanjay Gamwat. And that told how to search across this massive amount of data by searching in place rather than trying to bring it into a common area. These were radically new ideas at the time, and they really changed the whole concept of how you had to structure software and hardware. Now let's go to that same time frame, 2000, and it was a holiday season, and Amazon had been around for about 5 years. And they were starting to sell reasonably amount of good stuff online. And at Christmas time, they would get too many orders. They had a big front end and a big back end, the classic client server architecture of the time. And the server simply couldn't keep up. So they had to do something. The first option was to figure out how to handle more transactions, but they had tried and they had bought the biggest things they could possibly think of. And the second option was to break the transactions apart into little pieces with horizontal scaling, which was something that wasn't considered viable at the time. If you had a transaction, it had to be ACID. That meant all or nothing. It had to be atomic, all or nothing, consistent, isolated, and durable. And by breaking it apart, you didn't have all in the same package. So you weren't going to have your consistency. They chose option 2. They broke it into services, and they said, look, eventually we'll get everything consistent. For a few milliseconds here and there, it won't be. But what's the worst thing that could possibly happen? Somebody might buy something and it's not in stock, and we have to go apologize. That's not like looking at a bank account and discovering that you were wrong on how much money it was in. It's just something you can correct. So they decided that this concept of eventual consistency would work. Then, because they broke the transactions into services, given Conway's law and all, they discovered that it was important to organize into small teams that each owned a separate service and was responsible for making it work. Interestingly enough, services had their own data. They were not going to any central database. You know, when I first heard about this, I thought they were crazy. You had to have a central integrated database, or else they knew something I didn't know, and they did know something I didn't know. Services own their own data, and they are passed information by other services. They don't share their internal stuff with other services. Well, it turns out this was very hard on the operations people. So Amazon designed a self-deploy mechanism so each team could deploy their own software whenever they wanted, because there was a whole bunch of independent teams, like a whole bunch of independent teams. And so they needed to figure out how to let those teams own the whole system all the way through to deployment and support. And they did that. And that eventually became the cloud. So, for example, in August of 2006, mind you, this is 5 sort of years later that they were working on these services, they introduced the first part of the cloud, which was EC2, and sort of the rest is history. The current run rate of their revenue is $80 billion a year from having this concept of services and selling it as cloud services for basically nowadays a huge amount of all of the big companies in the world. Interestingly enough, not 6 months after Amazon launched ECT, the Apple iPhone was launched in January 2007. And this combination of cloud and phone became a whole new concept of how do we structure our architecture. So let's go into this concept that architecture is what allows you to scale. Okay? It's very important to think about it that way, because when you want to scale inside of enterprise, you're going to run up against your cathedral. And if you go to the bazaar style and change fundamentally your architecture to services, you then are able to scale. So if you take a look at the evolution of IT, let's start out here in 1999. You, at that point, had a thick client server on a thick client, a stack, operating system, runtime, middleware, monolithic physical infrastructure. That's what it looked like. And that's what everything looked like. And all of the internet companies had to figure out how to do something different. Now let's come to 2016, or probably even sooner, but let's just take that because this is from Docker, which is about the time that they got started. By that time, you had a thin app on a mobile or a tablet. You assembled your stack by using the best available services you can find anywhere, and you were running on any available physical resources, whether they were virtualized or public or private, whatever. That's what happened in that time frame, those 15, I guess this is 17 years from 1999 to 2014, let's say, 15 years. So that was a radical change. We went from enterprise to smartphone architectures. So here is what the enterprise architecture had looked like for decades, for I can attest to quite a few decades before the 2000 sort of cut off. And there had to be one system of record for a company. Here's what the smartphone architecture looks like. Every single app that you have basically has its data stored in the cloud and doesn't really share it with the other apps on the phone. In fact, that was the sort of first set of microservices, which we've now moved to other computers besides mobile phones. And the microservices have distributed data store. Each app owns its own data. And if you're going to share it, you're going to share it through the cloud. So basically, you have a cloud and mobile technology platform that became big in the early 2000s and went on from there. The other interesting thing about this is these services are local to me on my phone. I can hold my phone and I can see lots of stuff. I'll show you that in a minute. So horizontal scaling not only gives you a large amount of space to expand into, but you have local control of each service. Just like in those bazaar, you have each little stall having its own person that owns it and hires a few people and sells it, does their own pricing and sells their own food. Similarly, services, microservices are their own thing. In fact, Building Microservices, this is by Sam Newman, and he's just put out in the last year a new book about microservices, actually second edition of his great book on microservices. These are small, useful services that are independently deployable. You don't need permission from anybody, not managers. You don't need permission from your colleagues. You don't have proxies in between you and your customers. It's built by full stack teams. It's the concept that Amazon says is you build it, you own it. And the feedback is direct from the team to the customers. The practices you have are no central databases. You use APIs instead. And the APIs have contracts with each other on how they're going to behave. You have extensive automation for testing, for deploying, for monitoring, for measuring, and widespread knowledge sharing of techniques, patterns, tools, lessons learned, stuff like that. So we've moved to software engineering with APIs rather than big central databases. And if you think of API, it's an architecture. It enables service architectures, it lowers integration friction, and it has local persistence, which is really important. And it basically replaces those big databases we used to have. But if you think of APIs as a product, basically they are owned by a product owned by a responsible team that focuses on the customers of that API, and they evolve its capabilities independent of other APIs. So they enable the Internet of Things. It's something I'm going to talk about in a minute. So I thought I'd sort of say without APIs, we couldn't have the Internet of Things. So I would like to point out in conclusion of this section that scale is an architecture problem. When you cross that threshold from the cathedral into the bazaar, you need to completely change the way you think about architecture. It is not a process problem. If you think some large scaled agile process or anything like that is going to solve a scale problem, you're actually wasting your time on the wrong thing. You need to think about how can I modify my architecture to deal effectively with scale and allow small teams to operate independently. It's a different structure and it's a different way of thinking about how to grow. So it's time to move to the bazaar if you can't scale anymore in your cathedral. And then we started seeing things that were smart, that were virtual, and that were connected. Let's start with smart. There was a massive artificial intelligence breakthrough in 2012, but it had a lot of years coming. In 2012, there was a team at the University of Toronto led by Jeffrey Hinton, who'd been working on neural networks for 30 years. But the problem he had was his idea of neural networks couldn't be tested because computers didn't have the compute power to grind through all of the information in neural networks. Starting in the mid to say 2005, 6, 7, 8, 9, there started to be high-speed processing, and suddenly things like speech recognition became a reality using neural networks. And then late in that, about 2010, Fifi Lee, a PhD graduate who was starting her career, decided that the thing that might work with artificial intelligence is being able to train a database. So she created something called ImageNet and hired a lot of mechanical Turks in order to label all of the images. And then every year there was a contest called the ImageNet contest to see, they took a bunch of the images and put them out and said, what team can have their software identify what's in this picture? And in 2012, the University of Toronto team scored 16.4% error rate on the ImageNet challenge. That was an astounding 10% improvement from the prior year. And almost immediately, Google recognized that there was something going on here, and they hired both Jeffrey Hinton and Fifi Lee. And eventually, not too long from then, you started seeing things like TensorFlow out of Google, which is a neural network smart system. Not just artificial intelligence, but also virtual reality has also come into the plane. You can use it for things like, for example, is maintenance systems and teaching medical students how to do procedures you don't want to do unless they're needed, things like that. Now let's go to the third thing, which is smart connected apps. And I want to show you my mobile phone. This is virtually mostly the apps on my phone. This is Google Home, and this is my doorbell. This is my sous vide cooker that cooks my steak. This is my grill. This is our water system. It tells how much water we use. It's from the city. This is our big ceiling fan and our ability to control it by temperature. This, I'm going to show you a little bit more, is the monitoring for our solar system on our roof. This little system monitors temperatures throughout our house and gives us temperature and humidity. This one here is the thermostat for our fancy furnace with a heat pump. This here is our water heater heat pump, and we can see how much water we have that's hot and manage it. This is my vacuum cleaner. Here is our router. We can see all of the different things that are on our router. This is a synchronization for our HEPA filter to keep the house air filtered. This measures the radon in our house. We had a radon problem. This is CASA. This is our light switches. And these are some automated plugs that we have that are hooked into Google Home for us to control by voice. All of those things you kind of expect anymore. When you buy something, it's going to have its own mobile app, and you're going to be able to trace us. I'm going to show you, this is our solar system in our house. And you can see here, this is our battery, and it charges it up during the day, and then you can see it's using it at night. And this blue, that's how much solar power we are getting. This happens to be a good sunny day in September, but you can see black is how much we're getting from the grid, and you can also see how much we're giving into the grid, which is the blue, which is after we charge up the battery, that stuff goes to the grid. So this is just kind of normal today, but let me tell you, 20 years ago, it would have been radical. So in 2020, something happened to our house. Our cable modem failed for 2 days. We had to replace it. And so we had a nice smart home, and guess what? We couldn't use voice recognition. We couldn't use most remote controls of our light switches and our plugs. We couldn't do our shopping list, those were all voice. We had a video doorbell, didn't work. We had a vacuum cleaner, didn't work. We had some local control, but absolutely no automated control. This is not a great architecture. It turns out that there is an interoperability standard called Matter coming into effect that is going to allow compatible devices to talk to each other if they're Matter compatible, and hopefully allow a whole bunch more local control. But without local control, this thing becomes a very fragile system. So something to think about when you're thinking about expanding. Local is nice, but there also needs to be smart local edge computing, not just everything centralized. So let's talk about the new technology stack, okay? The new technology stack, we've moved from monolithic architectures to federated architectures. We moved from the databases being our big integrator to APIs connecting everything. We've moved from consecutive execution, one thing at a time, because, you know, big server, to concurrent execution of multiple things. So we can be doing several transactions at a time. We can even be doing several spots of a transaction because we're basically got services and we're stringing all the different services for that transaction at the same time. So you have to deal with that. We used to have mostly synchronous, now asynchronous. So Slack, that's asynchronous. Synchronous, telephone. Email, asynchronous. We went from procedure programming to event-driven programming. We notice things happen and respond to them. Actually, event-driven programming is what I used to do when I did process control programming, because we had to recognize when our equipment did something and respond to it. And now we're back to much more event-driven programming. Once upon a time, all the hardware had to be provisioned before you could have something working. Today, we have Lambda functions and things like that in the cloud. We don't necessarily even have to provision a server in the cloud if we choose to do functions. So pretty dramatic. You used to have these big data warehouses and they were considered really, really advanced. But today we have artificial intelligence and data warehouses are maybe not the right way to go anymore. We used to think that things had to be completely free of defects. And we've realized that what we really need to do is to allow defects and be able to detect and recover rapidly from them instead of making it impossible for defects to happen. So this is the enterprise legacy over on the left. But when we talk about the Internet of Smart Things, we have to talk about something more like we talk about what's more like on the right. And as we walked into the future, we're going to see more and more of this kind of stuff instead of that kind of stuff. Now, I have to admit that I put this whole talk together 4 or 5 years ago and haven't changed it a whole lot since. So maybe this future has become closer to right now, but you also can see projection of where things may go next. But I want to change a little and talk now about the engineering culture rather than the engineering advances. Because software engineering is not just technology, it's also culture. And I'm going to talk about 3 things: flow, feedback, and knowledge sharing. So in the area of flow, what we have learned is that we should build a continuous delivery pipeline, not a great big bang stuff where we get everything all ready and once a year we deploy. The radical book, Continuous Delivery, which came out in 2010, kind of changed the way we started thinking about how to deploy, from big bang to constant small things. And it's been improved upon by the DevOps handbook and Accelerate and that whole concept. If you're not doing continuous delivery, or at least continuous availability to deliver, today it's about time you got there. Because we have this problem that we've got these things called product managers or product owners or somebody like that. And half the time that person's going to be wrong. There's an experiment from Microsoft which shows that they did their product managers, and the product managers weren't any better at guessing what was important than the rest of the team. So why not continuous delivery with direct contact to the customer so the team can learn rather than having somebody tell them what to do next? And in fact, if we have features and functions in a big requirements document for a project, we have good evidence that 2/3 of those things are not going to be necessary. There was an interesting Standish report on that, and it hasn't changed. It's really not right to say, I know everything now, which is going to be needed, I don't know, 2 2 months from now, 5 months from now. I don't need to have feedback. I need to just do what this document says. Well, yes, you're going to do a whole lot of extra work then. It's much better to just be lazy and do what works for an experiment and continually feedback. We were in Japan, and one of our friends there was giving a talk to his colleagues saying, I joined a team. He was from Microsoft in Tokyo. And he said, I joined a team in Seattle remotely. And I discovered that one of the most interesting things about the team was that everybody was lazy. They didn't do what they were supposed to do. And it turns out that they were right, because you didn't need to do most of the things that you were supposed to do. So we in Japan, we're so diligent and get everything done we're supposed to do. We should learn how to be lazy. It was an interesting talk. So we need to move from delivery teams to problem-solving teams. So there you have it, a bunch of instructions, measure how good you're going against it. That's a thing of the past. We need to have teams that are given puzzles and figure out how to put them together. And we need not to be measuring how much output a team does, but what are the outcomes? What are the impacts? How does this affect the customers? And we need to have the team in direct contact with those customers without a proxy in the middle. So the team needs feedback. We're talking about full stack teams, and we're talking about learning that happens with the customer in the loop. So the concept here is to maintain a continuous two-way conversation with the market for your service, and constantly experiment and adapt it to make sure that it serves that market. So that means small multidiscipline teams. You have to have design and engineering and product and for sure ops, because the whole team has to be there. And it has to have a clear understanding of the intent of what's supposed to happen, good metrics, and I don't mean proxy metrics, I mean outcome metrics, and understand the constraints. It has to have freedom to act without permission from colleagues or from managers. There should be frequent, if not continuous, deployment to obtain feedback from the market. That's necessary to get the feedback. And we have to emphasize learning over delivery. We need to learn what customers are going to love, because we don't know to start with. The idea that you know is interesting, but almost never true. Not when things change as fast as they do in our world. And success is meaningful outcomes, not proxies. Proxies, not process, not features, not output, not people who tell you what to do. It's proxies that we want to get rid of and really measure, are we doing the job that we needed to do? And the third big important thing here is knowledge sharing. Sharing tools from others, sharing our patterns, sharing the techniques that we use, sharing incident reviews and the results that we learned from them, sharing integrating events, which I'm going to talk about in a minute, so we'll hold off on that. What I'm going to propose is that the future, we're going to see more of what I'm going to call the military model. Wow, what is the military model? So the military model, if you can see, we have small teams here, and they're grouped in groups of 3, and they form into a platoon, and they're grouped in groups of 3 with a weapons platoon. And then they're grouped into a company, maybe 250 people or something like that. And it goes on up in the hierarchy. I mean, we do big things. We don't just do small things. We don't just have single small teams. And knowledge sharing is for when we have lots and lots of bizarre type services. We still have to make sure that they work together. So in the military model, the first thing is it's important for everybody to understand 2 levels up from them, the command intent. That is a concise expression of why we're doing this, the desired results, and your little group, your squad, your team's progress towards the desired end state. You need to understand it not just from your leader, but a couple levels up to here. What are we supposed to achieve? It's your job to know that. And you also need to maintain situational awareness one level up. So if you're here, you need to know where your other platoons are. If you're a platoon leader, you need to know where the other two are. So here's this, anybody in this squad needs to know where the other two squads are so that they maintain contact and work together. And at this level, they're working together with the leaders, are working together with the leaders of the other platoons, and like that. And the way that the situational awareness is maintained is by briefing and then briefing back to make sure you understood what you're about to do when you're going to have an event or an action. And then when you're in the field, you need to maintain situational awareness. You need to know where the other squads and platoons, not just where they are, but where they're going and where they're going to be next. And you need to constantly adapt to make sure that the company reaches the end state because stuff changes. One of the ways that the military uses to make sure that this is learned by everybody and works is by rehearsing, by practicing, by doing exercises constantly in order for everybody to learn how to work together and get better. So this is a picture from How Not to Land in Orbit, really cool video about SpaceX and how, as it was learning to do landing of orbital rockets, they blew up quite a few of them. And you wonder, why would a company publish all of their mistakes? Well, the problem is that mistakes are actually cheaper and much better and much faster than getting everything perfect. So from 1970 to 2000, the cost to launch a kilogram into space averaged $18,500 in the US per kilogram. And then SpaceX started in about 2008 or 12, so 10 or 12, and started figuring out how to make stuff work. And by the time they got the Falcon 9 in 2018, the cost was down to $2,720 from $18,500 per kilogram to launch into space, a 7-to-1 improvement. And it's because they developed that landing rocket, booster landing rocket, really fast. And how they did it, it's really interesting. They did what I'm going to call integrated events. It's like they did launches, they were scheduled. And if the schedule, if you met the schedule and you did the launch and you learned, and if it blew up, you'd better have everything in place so you can learn from what caused it so that never happens again. That's part of your job. Because John Motori, their launch director in this time frame, he said, we can design, build, and test at a low cost. I mean, that doesn't look like a low cost blowing up on the deck, but they didn't hurt the landing ground. They only hurt the rocket. We can design, build, and test at low cost, so we can afford to learn through experience rather than consuming schedule, attempting to anticipate all possible system interactions. So this concept of what I'm going to call sync and stabilize is a name that was applied to it, sort of a name that we tend to use for this concept of integrating events is very regular events where all the teams get together and they do something that they have tried to do. And if they fail, they learn what's wrong. So constantly having people work together as a large group to find out how things work and what is wrong with the way things are going. And that builds both understanding of command intent and it builds situational awareness. So just to summarize quickly, the future of software engineering, then I'll have about 10 minutes for questions. The future of software engineering, or maybe today's software engineering, is about horizontal scaling. It's about the fact that architecture is critical and we have to pay a lot of attention to it. And we've got to continue evolving it. And we have to look at smart, virtual connected things and what it can do with that. We have to look at a culture which has a delivery pipeline, which people are directly connected with their customers, and that team makes the decision on what experiments to run next. We need feedback so that the team is directly connected with their market. And we need knowledge sharing of techniques, patterns, tools, lessons. We need briefings. We need situational awareness. And we need integrating events, which is also called sync and stabilize. So in conclusion, the future has arrived, and it is time for us to have some questions. So Tom is going to join me here, and I would like to say thank you.
Perfect. Thank you.
There we go.
Yes, so the one of the follow-up question right away. So I presume the military model doesn't mean teams losing their autonomy.
One of the most important parts of this military model is that teams have autonomy. They are trying to achieve the intent, not the specific detailed commands. If you take two armies and you have one that is operating with what's called mission command, they get missions and they figure out how to operate it at every level versus command and control. And you put them up against each other, guess which one wins? The one that has a lot of freedom at the team level to use their best judgment on what to do next in the context of the command intent. That's where the military model there's various models around the world, and you can actually see today which ones win.
Super. The other question we have, do you think that distributed teams with fail often and learn is the right approach for every sector?
I don't think that, I think a distributed architecture is probably important, but the teams do not need to be necessarily distributed or not, because when I think of a distributed team, I think of people in multiple locations. I think there's an awful lot of research and evidence that says that where the team is located is not particularly important. Whether it's co-located, whether there's several teams together, or whether they're spread out, the results tend to be very similar. What doesn't tend to be similar is teams that care, that understand the purpose, and that figure out how to make stuff happen. So if you look at Linux, for example, I mean, nobody was in the same room ever. And that operating system was developed by volunteers all over the world and completely without a central coordination. Well, there was a central coordination Linux Torvalds, and he was like the benevolent dictator, but he didn't tell people what to do. He just made sure that certain basic rules were followed, that committers reviewed code, and that people understood what was important. And it's that concept, no matter if people are together or separate, it's knowing what's important and believing in the mission and working to achieve it that makes teams successful. Where they physically are has proven to be interesting, but not necessarily important.
Oh, this is fantastic news, I think, for many of us working in all the different locations.
Right. Well, you know, during the pandemic, people got really, really good at that.
Yes.
And all of a sudden, wow, everybody discovered, you know what, this actually works pretty well.
Yes, absolutely. And then maybe also in a way related question is that regarding the knowledge sharing. So because we are in the knowledge industry, and in a way, the more good insights we share and experience and failures, the better. But do you see any emerging future practices or any proven good practices when it comes to knowledge sharing?
I think the incident review is a really important one, because the incident review, it's similar to the incident review that they actually have in the military. When you have an incident, whether it's good results or bad results, you get the team together and other associated people, and you talk through what's happened what went wrong, what went right, what we need to learn. If you have failures and you don't learn from them, then it's sort of useless. So you need to pause after doing something. I mean, you can think of a release review, where after you do a release, and let's say you release, let's say once a week, you have a release review, that would be like a retrospective. This concept of pausing and looking at, how did this work when we had this activity? What went right? What went wrong? Who did what? What can we do better? What can we do better the next time? And action items which make things happen, I think, are the most important part.
Do you have any
The other part that I think is really, really, really important is the direct connection of people working on creating new software and the people who are using it without an intermediary. I mean, we have a history for the past 25 years of having somebody in between a development team and customers. We went through this whole agile thing, and we called this person a product owner, and we had them figure out what the team should do next and set their priorities. That's just wrong. Okay, that's the worst thing that Scrum has visited upon the software world. We need the team to be deeply engaged in getting the customer outcomes that are desirable, knowing them and achieving them, not having somebody in between figuring it out. That's just a wrong structure.
Yes, we actually had very related question to that Andy is asking. How about like moving from delivery teams concept to problem solving teams concept? And that's what you are sharing. Do you have any like resources or maybe concrete case studies that we can all like be inspired, take into our companies and say, this is how it should be done?
That's hard. I want to do, but it does trigger a story. I was in Oslo and we went to a bank and we were talking about, I think probably something similar, because this is not new for me. And there was a woman in the room. There were maybe 20 of the software developers. And she said, I have been writing code for a very long time. And it used to be, before Agile arrived, that I was expected to figure out what to do and be engaged with the customers. And now Agile is here, and all of a sudden, I don't get to do that anymore. And I could do a lot better and be a lot more productive and a lot more useful when I was engaged in figuring out what to do, rather than having this process, which causes me to have to, take somebody else's word for what's happening. That is just not a good concept at all. I don't know, however, how to convince companies of that, because when companies have in their head something that they want to do and they think they've been successful at it, then it's really hard to get it out of the heads of managers. Or the alternative, if companies are struggling and they're looking for advice on what to do, if they get the wrong silver bullet, here's a process and it's going to solve your own all of your problems. I can say all I want that it isn't going to work, but they apparently have to figure it out for themselves.
The critical thing is not what you do. What you do is process. And we have been working in the Agile community for 2 decades to impose a way of doing things. And it has utterly failed to make much difference. What has to change, and this was well understood way back in the 80s and 90s, is not copying what other people do, not copying processes and practices. Processes and practices are interesting ideas. They may or may not work for you. What you have to copy is how people think. We have never seen an organization in the manufacturing world successfully become lean by copying what Toyota does. Copying what Toyota does means you're adopting their solution to their problem in their context with their current people. And if you don't have the exact same context, their solutions are not going to be the right ones for you. Same thing is true in software. Copying things that other organizations do is not going to solve your problem. Looking at how the organizations that have become dominant in the software universe and seeing how they think, and contrast that to how the atrophying, dying organizations think, gives you guidance about how to proceed.
Yes, if I had one mantra, it's think for yourself. The companies that we have dealt with that either didn't know about Agile sort of early on, or pretty much ignored it and thought for themselves about what they needed to do, have uniformly been the ones that have been very successful. It's not a guarantee, but you know, following other people's solutions to their problems is a guarantee you're not going to solve your own. If you could figure out how to make all of your very smart people that are software engineers think and be engaged in making your company successful, then you're leveraging the brain power of everybody, not just a few people. And the only way you can get really good is to leverage everybody's creativity and brain power. And we haven't done enough of that, and we need to do more.
I think this is spot on ending for this session. I love that you paid attention, that we should get the most from everyone, not just from decided in the role, and yeah, encourage everyone and to learn how to think. That's a very good advice. So I wish you a very good December and the beginning of the new year. Thank you for the talk and joining the Q&A, Tom, and wish you all the best. Thank you.
Thank you.
Thank you.